So thank you all for being here. This talk will be slightly different from what we've seen today, but thanks to some discussion that we had earlier, there will be many common points. So the idea here is to show you some use cases where we do use symbolic execution for reverse engineering and security assessments that we do. And as Peter mentioned earlier today, while we do that, we want to be more productive at some point. So we use symbolic execution whenever it's suitable and makes it more effective for us to do our assessments. But for today, I'm going to focus on the two main use cases that we encounter in our daily tasks. The first one is obfuscation, and the second one is more exploration and fuzzing. But then I will quickly explain how we do use also symbolic execution to further research and find new tricks and techniques. So obfuscation assessments. This is a huge part of the things that we do at Quarkslab. And the question is, the use case is, okay, so we have clients that want to make sure that the obfuscation that they apply on their products is indeed robust. So they ask us to break them. And we also use it to also help improving our own obfuscator. That's another story. So obfuscations now today is like everywhere. In payment solutions, in mobile applications, in DRM, like everywhere. There had been a lot of works on breaking some techniques like opaque predicates and virtualizations, but as we only have 15 minutes, I will not have the time to discuss them. So we will focus on one transformation, which is called Mixed-Boolean Arithmetic. And the obfuscation is the following. So let's take this small A plus B, you can obfuscate it into by adding some bitwise operation and arithmetic on that expressions to make it way more complex to understand. But yet they are still symmetrically equivalent. So we can obfuscate it, but the question is, how do we get the operation back to retrieve the original expressions? And this is where symbolic execution comes into place. And the techniques I'm going to present here is the one I designed with combining symbolic execution with program synthesis in order to retrieve the original expressions out of the obfuscated one. So if we have your assembly on the left here, you basically execute it with your favorite symbolic executor. You obtain with your IR the semantic of the expressions, from which in our case, we are going to extract the data flow expressions of the expressions that we want to consider. So here it will be array-x. So our input for the rest of the algorithm will basically be the AST of that expression, which encode the semantic. And the question is, how do we simplify that into the original one? So in our context, we solely use symbolic execution as a means to extract the data flow expressions of or such registers, memory, whatever. And from that, we are going to do the rest, which is the synthesis itself. That I will also quickly describe because are very short in time. So once we have executed symbolically the code, we obtain our expressions. This will be the input for our synthesizers, and hopefully we will obtain something which is reduced. And the old algorithm that we wrote is basically combining two different components. One is tree traversals to try to simplify sub-expressions, like sub-trees at some point, combined with the input-output oracle. The idea behind the oracle is that you're going to evaluate your expressions on the sets of inputs, from which you're going to obtain some outputs. And if at some point this output vector is the same that a set of pre-calculated ones that we have done beforehand, we can assume that they somehow behave the same way and they are symmetrically equivalent. And if so, you can replace the expressions by the more simple one. Okay. By the way, that's not, this is a bit heuristic. So you can also reuse SMT here to check the equivalence of the expressions that you synthesized. So that's basically the idea of our de-obfuscation algorithms, where we mix both symbolic execution and program synthesis for simplifying expressions. It actually works well on various use cases. This is an expression that we extracted from some chat applications on mobile phones. So it's very useful to simplify some expressions that have been obfuscated. Now with all the derivative of the LLVM-based obfuscator, like we have many of these things nowadays. And there's a former colleague, which is called Roma, that also showed that Android is also using it in safety net to hide some operations that are being performed to contact with the Google server. So yes, in this context, as obfuscations have to preserve the semantic, and because symbolic execution is all about manipulating the semantic of the program that you're executing, this is indeed a really suitable approach for the obfuscations. So that was the first use case that we use a symbolic execution a lot for. The second one that is more into the thing that have been discussed beforehand, and actually it will echo a lot with what Frank showed this morning, is some program explorations. And this is another use case that we have with some of our clients. The idea here is to use symbolic execution as supports of some fuzzing. And the industry problem is that some people want to analyze their code before it getting shipped to their clients or their device or whatever. And for some compliance and security, they want to analyze it to make sure that it's somehow okay. So what they do for that, they usually use static analyzers to analyze their code. And indeed, as we already mentioned earlier this day, these analyzers yield lots of alerts for which you don't know if they are false positive or like true positive. So the question is how we can figure it out. And this is where fuzzing and also symbolic execution comes into place. In our use case, we are using Clockwork because Clockwork is like now like a de facto standard in many industries because they implemented lots of dedicated checkers for like Misra, AutoZar for like automotive things. And people, as it's for them like a pain point to make sure that their code is safe, they just take the software that everybody is using, and so everybody, at least everybody has the same issues. So they work for many languages, so and that would be our input because we had that as an input. So this is the kind of reports that we obtained from the static analysis. Unfortunately, at that point, they did not yet discover the serif format to make the results processable, but that's not a big deal because it's HTML. So what we do is basically we take the report, we convert it to JSONs to make it reusable by our own processing tool. And in that context, we also have to mention, we also have the source code. It's not always the case, but we have it, so we can leverage it. And the idea is that for each alert that we encounter, that we have in the report, we are going to add an intrinsic functions into the program. So for our key users, that should be like a familiar thing. That will call dedicated functions with some parameters. And this is what is interesting in our case. Here the parameter will be like a unique ID, the type of the issue that has been raised by the static analyzers, and some additional parameters. So here, if we are considering an str and copy, we are going to provide some parameters. And here we cannot see it clearly, but it's the size of the destination buffer. This is very interesting because at binary level, this is the kind of information that is lost. So if you encode it as a parameter of that function, you will be able to retrieve it at runtime, basically. So doing that has two advantages: that it allows you to precisely locate the alerts into the binary, whether it has been duplicated by means of inlining or something. And also the output of the functions is just a print on std out. So if you just look at the output of the program, you know which one you've basically covered. So what we do with that is where we are trying to combine fuzzing and symbolic execution. Why doing that? Because fuzzing is like basically fast to cover like a huge part of the space of the program, but it will not be able to reason about all these interesting functions that we have added. But on the other hand, the dynamic symbolic execution will be able to do that. And we are able to write like dedicated like symbolic checkers on these functions calls that we are going to hit during the exploration. And the corollary issue is how to combine them efficiently, but that's a whole other story. Just to give you a small idea of that, so we have our intrinsic functions, and when we hit that functions, we are able to write basically our own symbolic checkers. So the first thing is just to check if the violation is taking place by looking at the parameters. So here we're just retrieving them, the 2, 3rd, and 4th, which are the side of the destination, source of the end. And if there is no violations taking place on that path, actually with symbols, we can also try to encode if a violation can take place. And for violation to take place with str and copy, we have to make sure that the size is bigger than the destination buffer, and also that every bytes of that buffer are different from 0. Can be different from 0, and yes. So that's basically the things that you can implement with that. So if I just sum up very briefly the whole workflow, we have our source code. Obviously, the hardest part in every fuzzing campaign is to write the harness to be able to target the specific components into the programs that you want to test. And then you run your static analysis software tool from which you obtain the reports. You insert the intrinsic functions into it. And the things that we try to automate as much as possible is compiling it for like every target fuzzer, running them, making them to talk with each other as much as possible, and then the output is the reports of the alerts that have been covered and the ones that have been validated. Obviously, you just cannot prove an alert to be a false negative because it will require you to cover all the path, which is not possible. But at least it has some, it's great because it still helps the analyst to just focus on the ones that are still not covered and still not validated. So it's like pruning a lot of them, and this is making you save sometimes, basically. How we are combining fuzzing and symbolic execution here. So we are doing some what it's called now like ensemble fuzzing. The idea of ensemble fuzzing is that you're going to combine some heterogeneous testing tools to make them collaborating. We say fuzzing tools here in the broad definitions as Michael mentioned this morning. So we are more talking about like testing tools here. Okay, and highly behind that is that no fuzzing tools is better on every target. It highly depends on the structures of the code, of the mutations and memory parameters that comes into place. So that might be valuable to combine them. Okay. Obviously, there has been a lot of some research on that topic beforehand. In our case, we wrote our own tools, which without surprise is combining Triton, which is our own symbolic executor, with some fuzzers like HomeFuzz and AFL++. It's rather simple. It's just like it's written in Python. We made it so that it's all network-based, so the engines can be just communicate over the network. And we added some features to be able to replay the inputs to make sure that we indeed cover the intended path and so on. We found the main target in our case were TCP/IP stacks because they are critical components, and we have been able to find some issues on some of them. That's the rough architecture of the whole thing. We have a broker here that is going to take as inputs the reports, all the binaries compiled with the different instrumentations of the engines, some configuration file, and then you're going to have all the engines that are going to connect to the broker, retrieve the binary, and just fuzz. So what you have to do here is to just write your driver that you can get with the broker and send them the inputs that you've just found. And it will be, we can implement many strategies. Here, the strategy that we use is like doing maximal sharing of all the inputs. So as soon as the input is found by one, it will be propagated to the others. So yeah, that's the idea of that. I cannot do a demo, but if I had my laptop, I would be able to do it. I think I have plenty of time. So that was the two use cases that we often have concepts where we do apply indeed symbolic executions, but we also use symbolic executions to feed our own research, internal research. So the base is mostly Triton, obviously, but at the top of it, we've been able to develop like many components at the top. And the one that we worked on for a few years now is the Triton DSE, which is basically, so as Peter mentioned in the keynotes, Triton is like a really low-level components that you can really integrate easily with dynamic instrumentations or anything. But it requires you to implement like many additional things if you want to do more sophisticated things. So this is basically what we are doing with Triton DSE here, is that we are doing the exploration, the program loading, all these kind of things that we want that makes it more close from Manticore now or KLEE or this kind of symbolic executors. But that allows us to also do some experiments, like we have our own heap allocator so that we can play with that. We are doing some basic multi-threading supports to be able to schedule them the way we want, basically. And obviously, we also have to stumble upon all the symbolic stuff that you have to implement to do that. Hopefully, it will be open source soon, because we have no good reasons to keep it internally. So yeah. And there's many ongoing experiments. We have here Richard, which is doing some internship with me, that is exploring many things with that. Obviously, when you have alerts or assertions in your program, you might want to do some directed approach. That's something that would be useful. We don't do that at the moment, but this is something that we are obviously studying. And with all the frameworks that we've built, we are now able to experiment with like the seed scheduling strategies, like seed sharing strategies between the engines. There's many things that we can play with to assess whether it's like relevant or not. And we are also leveraging the full disassembly of the program. So at some point when you want to do more sophisticated analysis, you want to have the whole topology of the programs, have the full representations. And because Triton does not that by default, actually we are using the disassembly of IDA. And we have a dedicated exporter that we use for that we also probably going to open source soon, which is called Quarkslab. And it's basically taking the whole IDA disassembly, export it to a file, and you can reload that file in your own analysis to basically manipulate the program as it's disassembled into IDA. So there is many things going on these topics that we try to explore. Richard recently integrated Triton DSE into FuzzBench so that we can do more academic benchmarks, let's say. And so that will allow us to do way more experiments on Triton DSE. Very briefly to conclude, so for symbolic execution is very handy for us. We use it whenever we can and whenever it makes us save some time. Doing symbolic execution also helps us to find new ways to tackle problems that we encounter. The obvious ones, obfuscations. When we encounter new obfuscation, we try to find ways to break it. On some specific targets, also doing like very low-level symbolic execution on specific components also helps, like in embedded systems and things where it's not like traditional P or ELF binaries. And there's also like all these research questions like that we're also investigating to know whether we have answers or not. And that's basically it. So thank you. If you have any questions, I'll be happy to reply. Yes.